All right. Good afternoon, everybody. My name is Giuseppe Cataldo, and today I will be presenting the new Apollo, a new generation integrated human robotic mission to establish a radio observatory on the far side of the moon. First, we will describe the motivation, scientific rationale for this project, and then we will describe the details of a preliminary design that we did for this mission. Then we'll move on to the systems architecture. We'll talk about the guidance, navigation, and control, human factors, safety, power, cost estimates, and we'll conclude with the main findings of our research. The goal of our mission is to set up a radio observatory on the far side of the moon with an integrated approach which will see both humans and robots cooperate in this endeavor. Why are we interested in a far side lunar observatory? There are many questions about our universe which are still unanswered. Namely, we don't know what happened between 380,000 years and 400 million years. We don't have any data. We don't know what really happened during that time. That's why we call this period the Dark Ages. We do know very well what happened before, during inflation, what happened afterwards, but we don't know really anything about the Dark Ages. So there are many questions actually that we are really interested in. For example, how did the first stars form? How massive were they? What was the role played by black holes in galaxy formation? How did stars and planets form and evolve? All these questions have been addressed partially by many NASA missions, such as the Cosmic Background Explorer, which won NASA Nobel Prize, WMAP, and many ground-based observatories, such as ALMA. So the answer to all these questions comes from a mapping of the hydrogen distribution in the universe, which can provide constraints to the current cosmological models. In order to do that, we need to work in the radio band of the electromagnetic spectrum. So the proposal is to establish a radio observatory on the far side of the moon for three main reasons. First, the moon can act as a direct shield against radio frequency interference caused by satellites orbiting the Earth, but also a radio emission generated by the Earth itself, the Sun, and also big planets such as Jupiter. Second, the lunar surface is a stable platform itself, as opposed to an orbiting satellite. And third, all the undesired radiation from the Sun can be avoided for 14 days. So if we let the radio observatory operate overnight, we can do our astronomical observations. And then maybe if we want to use the other 14 days when we face the Sun to actually study the Sun itself. The preliminary design that we did sees hundreds of self-standing array node and communication elements form a large lunar radio array. Each antenna unit is made of, is basically a helical antenna. Up to 7 antennas make a station, and many stations together will form this interferometric array. The working frequency will be the between 50 and 150 megahertz, and why did we choose this kind of design? Well, basically because we can stow all these antennas in very small packages, only half a meter tall. We foresee a lifetime of 3 years and a maximum baseline of about 5 kilometers. We really need this kind of antennas also because of the highly symmetric electrical field that this type of antenna can generate. And also we can use lightweight and strong materials to build them. So many advantages in building this type of antenna units, but also many challenges and constraints that we really need to take care of. Well, namely, we think that about 200 antennas will be useful as a first test bed on the moon, but many more antennas will be needed in order to study and analyze the dark ages and the epoch of reorganization of the universe. Many trade-off studies also remain to be made as to communications, data transfers, transfer to and from the Earth. Also, how are we going to operate, maintain, and service this observatory? And finally, we're still unsure about the capabilities of robots on the moon. So how are they going to operate and maintain such a vast array? So now we'll pass it off to Marcus.
Okay, thank you, Giuseppe. Good afternoon, everyone. I'm Marcus, and I'll be presenting to you the overall systems architecture for this project. So I'll be covering 5 main segments, and they are the mission architecture itself, which consists of the launch and rendezvous sequences, the launch vehicles, the crew exploration vehicle that will carry the astronauts, the lunar surface access module or the lunar lander that will carry the cargo, lunar roving vehicle, and finally we will choose a moon landing site. So we will propose a solution to every component listed here, and we want to integrate them to develop the overall systems architecture. So the first thing we will do is a 1.5 launch Earth orbit rendezvous and the lunar orbit rendezvous. So you have, why is it 1.5? So 1.0 represents the heavy cargo launch vehicle, which is over here, and the 0.5 represents the lighter crew launch vehicle. So the heavy launch vehicle will carry the lunar lander, and the crew launch vehicle will carry the crew. Yeah. So what they'll do is, upon launch, they'll then perform an Earth orbit rendezvous here, and the Earth departure stage will take the combined modules together from Earth orbit all the way to lunar orbit through a translunar injection, and the lunar lander will then undock, and they'll perform a power descent insertion here, and where they'll land on the designated site. And finally, once upon completing the science mission, they will then go back up again to lunar orbit and dock. And finally, they will return safely back to Earth. So with that in mind, we now choose the launch vehicles. So what we have proposed for the cargo launch vehicle, we want something big. We propose to use the SLS. So we are using the Block 2 cargo, 130 metric ton SLS to carry the lunar lander. And for the crew launch vehicle, it's going to be lighter. So we are proposing to use SpaceX's Falcon 9 Heavy, which has a payload capacity of 53 metric tons. So right now we choose the crew exploration vehicle, and we are proposed to use NASA's Orion spacecraft that came as a result of Project Constellation. So Orion has 4 main components: the crew module, service module, launch abort system, and the spacecraft adapter. The crew module will obviously carry the crew, and the service module will contain the propulsion systems, life support systems, as well as power sources. And the launch abort system will allow the crew to abort the mission and force a safe landing in the event of any mishap. And the spacecraft adapter is to overcome any differences in sizing between the launch vehicle as well as the spacecraft itself. So, as mentioned before, the crew exploration vehicle will be carried by the Falcon 9 Heavy, which has a diameter of 3.66 meters. And looking on the left, we can see that the largest diameter across the Orion is about 5.33 meters. So there's a difference in diameters. So, which is why we are proposing to use the spacecraft adapter over here. And we are not using all 53 metric tons as well. We are going to apply a 20% safety margin as a buffer. So we're going to set the mission payload capacity to 42 metric tons. So in terms of an approximate payload sizing, the unmanned Orion spacecraft is about 31 metric tons, assuming every astronaut to weigh about 80 kilograms, 4 astronauts will weigh about 320 kilograms, and the equipment has been assumed to weigh about 3,300 kilograms, and that will give a total of 35 metric tons, which is well within the capacity of the Falcon 9 Heavy. Next, we'll move on to the lunar surface access module. So we are proposing to use the Centaur vehicle. So what is the Centaur? The Centaur is essentially the modified upper stage of the Lockheed Martin Atlas V rocket. And what is different from the other modules that we have seen in the Apollo program is that it performs a horizontal landing similar to that of a helicopter instead of vertical landing. So the Centaur will be carried by the 133 metric ton SLS, and it will deliver the 4 astronauts, lunar roving vehicle, as well as the cargo to the lunar surface. So the Centaur consists of the ascent module and the descent module, and the ascent module will carry the astronauts with the necessary airlocks for deployment onto the lunar surface, the life support equipment, scientific instruments, and the descent module will carry the liquid oxygen hydrogen propellant, insulation for cryogenic structures, the cargo as well for the antenna units that we are bringing on board the lunar surface, and the lunar roving vehicle that will be responsible for, that will allow the astronauts to bring the antenna units from the vehicle itself to their designated deployment locations on the moon. And we did payload sizing again. The vehicle frame has been found through literature to weigh about 4.3 metric tons, the crew 320 kilograms, the LRV about 300 kilograms based on an inflated estimate, because the LRV used during the Apollo missions weighed about 210 kilograms, given current technologies, and maybe a trailer to actually carry the antenna units, it might weigh about 300 kilograms. The cargo, we are bringing about 200 units, and we are estimating each unit to be about 100 kilograms, so that gives us about 20 metric tons. And the liquid propellant about 40 metric tons, because we have used the rocket equations to find out how much propellant is actually needed to perform the powered descent from low lunar orbit down to the surface, and from the lunar surface again back to lunar orbit. So that's about 40 metric tons, and it's a total of 65 metric tons, which is well within the 130 metric ton capacity of the SLS. So right now we choose a moon landing site. So as you can see over here, there are two potential landing sites on the moon, on the far side of the moon, and they are the central far side highlands and the South Pole Aitken Basin. However, as mentioned previously by some other groups, the poles on the moon have unique environments, and it's because the sun is always low on the moon horizon, and this creates permanently shadowed areas that might contain ice, and the high ground on the south poles are always in the sunlight, so we can potentially set up solar panels and arrays that will power our equipment. And since it's relatively unexplored, and we have the potential or prospect of finding ice and performing new exploration, it provides potentially high utility to science. As such, we propose to land in the SPA basin and probably a flat crater just for safety reasons. And now, I'll just summarize what we have done. So we are going to use the SLS as the Falcon 9 Heavy, and we're going to launch the Centaur and Orion into low Earth orbit, and you'll perform the translunar injection based on the second stage of the SLS, and the Centaur vehicle will then undock, and you'll land on the lunar surface after 7 days of the mission. You will then perform the low lunar orbit rendezvous again with the Orion, and finally, we will return safely back to Earth. And now, I'll cover the guidance, navigation, and control, and this will allow the safe, accurate, and reliable maneuvers for docking, trajectory, and orbital maneuvers, and landing on the lunar surface as well. So the main focus of what we are looking in GNC is optical navigation, and the overall navigation architecture is shown here, and this is based on the Altair spacecraft. So two new things that we want to look at as well are the terrain hazard detection system that will allow the Centaur to be diverted to safer sites, incorporate the terminal descent radar system as well to estimate surface relative altitude and velocity, and the more usual components like sensors and thrusters to perform correction burns, Earth-based and onboard navigation systems to estimate position and velocity state vectors, and finally, the most obvious of IMUs with accelerometers and gyros. So a little more about the optical navigation system. You will leverage advanced optical navigation technology instead of relying on human memory, and this is to prevent any human errors that might result. And we actually saw that during the Apollo missions as well, where astronauts had to memorize and identify lunar landing locations based on sight. So the optical navigation system will allow star tracking, rendezvous, proximity phase navigation during important phases like the EOR and LOR. And it will also serve as a backup if ground support is lost. So we propose that optical navigation be used for both the Orion and Centaur vehicles. And now I'll pass it on to Cameron, who will talk about human factors and system safety.
Cool, thanks. Hey, I'm Cameron. I'll be talking about system safety and human factors, two obviously very important items for our mission. Now, human factors itself obviously incorporates a bunch of different components. It's a vast spectrum, and we were only able to just glance the surface of this. But one of the things that we looked at was making sure that the handling qualities of the vehicles were all right. We planned to automate as much of this as possible, but we wanted to make sure that manual backup was more than adequate for the pilots. So one of the things that we looked at was manual control for the Orion crew excursion vehicle. And this was the Cooper-Harper metrics of manual docking. 10 test evaluation pilots were used in this. So they looked at this through Cooper-Harper metrics and also a NASA TLX. And they found that actually this was a pretty easy task for the pilots, given all the displays and feedback given back to them, and actually no handling quality issues were actually discovered as a result, even when certain errors with the RCS, center of mass uncertainties as well, were thrown into the task of docking with the ISS in this case. This is just a mock-up of the Orion. Obviously, it's bigger than the Apollo crew and service module was, and it seats 4 astronauts inside of it. And obviously, they were able to build a mock-up of that, but the Centaur still resides on paper. This is just the landing sequence. I'll quickly go through this. The novel item of this is that the 2 RL-10 boosters actually slow it down, and then it actually lands horizontally. And the pilots are actually at the bottom of this. So you can see here 2 pilots, and they're given a panoramic view of the surface. So they'll come in a hover mode, but the actual landing profile allows them to land with a non-zero forward velocity. And then also, you see a descender module here, and then you see an ascender module right there. The ascender module can abort at any phase during the landing, and the ascender is actually what is used to rendezvous with the Orion back in orbit. So just a quick picture of these surface operations. We're giving the astronauts 6 days to deploy the 198 antenna units, and also the assistant robotic vehicles. And in the nominal case, there would be 2 astronauts going out on EVA, while 2 remain back in the Centaur to do diagnostic checks for this. And then we left the specific schedule up to the astronauts to give them the discretion to do that. So here's just a rough look at the Centaur itself. Ease of cargo access in there. There's 8 movable solar panels in there as well. More than double the habitable volume of Apollo, which is nice from the astronauts' perspective. And here's just some of the other characteristics of Centaur. But also talking about safety engineering, this is huge. Even today, NASA is huge on probabilities for assuring safety. I know just last week, Kepler lost its second reaction wheel, and it's now sitting in space with a 95 megapixel camera. Pretty much useless because it can't lock on to specific targets. So safety is something that we can actually engineer into the entire system, and we propose doing this through STAMP. Actually, Dr. Nancy Levison in this department, she pioneered this systems safety engineering approach to pretty much define safety requirements and constraints that can be enforced throughout the entire system to enforce safety down to the lowest levels. So in terms of our mission, the top level accidents that would mean success for safety would be preventing these 5 items from occurring. And then from this, you can refine this into safety constraints that you enforce throughout the entire system, socio-technical system from the highest levels of management down to the lowest levels of software code. So I'll turn it over to Dan right now, who's going to talk about battery options and cost.
Okay, so as Cameron just mentioned, I'm Daniel. I'm going to talk about power and cost. So these are some of the power options that we examined for the mission. So we didn't just arbitrarily choose, we're going to use solar panels. We actually went through this in some detail. So I'll just briefly go through them. Basically, batteries are simple, but they have terrible energy density at high scales, and also they do run down. We want this to be a long-term mission, so for the antennas, these weren't usable. Fuel cells, they have the advantage of providing water and heat, but they also run down after a relatively short period of time, a few weeks, and we don't need the water and heat for this mission. RTGs are basically nuclear batteries. They have the advantage of having manned flight heritage on Apollo missions. This is a picture of the RTG that powered the Apollo 14 ALSEP. All the ALSEPs used RTGs to power their instruments. The downside, and the reason why we didn't use them for this mission, is because they don't scale well, meaning that because they need so much shielding, it's hard to build a really small RTG that's still mass efficient. And we didn't think it was feasible to build a gigantic RTG with a lot of cables to all of our different antenna units. Nuclear reactors, also like the RTGs, are obviously political problems, and we also just don't need the high power and heat capability of a full fission reactor on the surface for this mission. There's also active solar power systems where instead of a solar panel, you have parabolic reflectors that reflect light onto a working fluid, and then you get power by driving usually a turbine or something. But it's more complex than solar panels, and again, we just don't need that high power capability for our mission. So eventually we settled on solar panels. They do have the long flight heritage on lunar missions. They're well understood, and they do scale very well. And because these antennas don't require a great deal of power, they were appropriate for what we were doing. They do have awful energy density if you want to scale it up. They very rapidly become non-competitive with virtually any other energy source, but again, our antennas are low power units. They do degrade over time from radiation and dust, so we would have to scale them to be slightly higher than 100% power requirements at the beginning of the mission. They can jam and tear on deployment and so forth. So these are issues that would have to be addressed in an actual mission. We size them using this calculation, assuming a certain efficiency and cost. Basically, the takeaway is that the solar panels are a minimal part of the price and the mass for the antennas for the mission. The other aspects of our architecture, Orion uses solar panels. The lander, this was NASA's Altair concept, but also the one that we're looking at uses fuel cells, and we have a small unpressurized rover vehicles that are battery powered, as on Apollo. This is our cost estimate for the mission, including the launch costs. SLS launch has been cited around $500 million. SpaceX cites the Falcon 9 Heavy cost of $54 million, but they have a long history of lowballing their cost estimates, and that combined with inflation, we estimate that it'll be a little bit more. We have a relatively minimal technology development cost because, again, the antennas aren't really anything technologically new. It's more a question of where and how they're being used. And we have a reserve cost also, and this ends up being, with launch costs, about on the scale of a NASA New Frontiers mission, just under $1 billion. That's sort of their mid-range mission between the lower-end Discovery missions and the high-end flagship missions. So in conclusion, we propose to set up an LRA on the far side of the moon. We've discussed our system architecture for deployment. We're using basically optical navigation for GNC. We talked a little bit about some of the human factors issues. We talked about how we arrived at the decision to use solar panels and how we size them for the antenna part of the mission, and we discussed how we came up with our cost estimate. And we hope NASA will approve this mission. And with that, we'll take questions.
Hi.
Yeah, that's just for the, recording.
Oh, okay. Yeah, really nice presentation. What's your plan for data downlink from the antenna, given that you're on the far side of the moon?
Well, we plan on using a correlator for each station, and then transmit data to a satellite in Earth Moon L2, which will transmit all the data back to Earth.
Is that antenna, that satellite, part of your cost structure? I mean,
Well,
what does it exist now, or are you planning on building it as part of this?
No, because it's part of the trade studies that we talked about during the presentation. It can be either this option or another option we talked about. We thought of was also having like multiple antennas on the lunar surface that can transmit the data back to Earth without having the satellite. All comes down to what astronauts and robots can do in the future. We really want them to cooperate together, work together on the surface. So it's an open trade-off for now. So that was not included in the cost estimate.
So does this require a precise location of the antennas, and how do you accomplish that?
Yes, the distribution of the antennas on the lunar surface depends on the spatial resolution and the quality of the images that we need from space. So what we determine, we need an angular resolution of 3 arc minutes to accomplish the task of probing in the dark ages. Once this number is defined, we can define more in detail how to distribute these antennas on the lunar surface. The calculation has not been done. What we did was to study the electrical field pattern distribution for each station. And then from there, we need to calculate the power and the spatial resolution and calculate the optimal distribution of the antennas on the surface.
How precise do they have to be located? Once you get that pattern established,
Right.
and you're on the surface deploying these, does it matter within a few feet exactly where they are? And how would you actually navigate to that location, put that antenna down, and do the antennas, have some way of measuring the distance of separation that they have? I assume you want precise measurement between each
Yes.
node.
So they can tolerate differences of a few centimeters. It's important for the antennas to be perfectly level, like lie horizontally on the ground. And then, as you mentioned, it's important for them to communicate. So we envision either a laser or optical fibers or avalanche photodiodes to use for the antenna to communicate with one another. And for the positioning, we envision this to be done by the astronauts in the beginning. So the traveling antennas will be positioned by the astronauts, and then the robots will position the rest of the antennas over the entire surface. Yeah.
I'm not sure if I quite understood. You put up a number of 100 kilograms per unit.
Yes.
And then you talked of 1,000 or 10,000 units. Is that correct? I mean, that's a lot of mass.
No.
Well, no, 198 was for the initial test, but for the final configuration, they're talking of 1,000 to 10,000.
Yes. So.
What I don't, for the individual unit,
Here.
I'm wondering. I mean, 100 kilograms strikes me as quite a lot of mass. What actually goes into that?
Well, we assume the antennas to be made of aluminum because it's like a conductor. It's quite light weight. So these are 8.7 meters tall, and then we need to include also the boxes. So in those 100 kilos per unit, the boxes are also included, as well as the truss structure that is not shown in here, which is needed to support the antennas vertically, as well as all the the correlator in the middle. Okay, so putting everything together will give the number. So we estimated a total of 198 antennas for the first mission, and that's good for a first phase. But we need at least 800 antennas in order to perform actual science. So further launches will be needed in the future to increase the size of the observatory.
Questions from the class? Did you have one?
Yeah. I have a couple, but I just wanted clarification. When you're saying that, when you're talking about one unit, it kind of looks in that picture like it's 3 antennas connected. Is that 1 unit, or is that 3 units in that picture right there?
So the unit is the single antenna, and then the unit per stand is the number of antennas put together.
Oh, okay.
So this is like a stand made of 3 antennas
Right.
per unit.
Maybe Marcus, could you say a little more about the horizontal landing and what the issues are in getting that to work? Because it's not included in your technology development costs, but it strikes me there's a whole vehicle there to create from scratch.
Yeah. So the Centaur vehicle is basically a conceptualization of or modification of the LS5 rocket, the upper stage of the LS5 rocket. So we sort of envision it to be like a semi-helicopter kind of vehicle. So you'll be able to land horizontally with a non-zero forward velocity. So it's not going to be like a space shuttle that requires a runway, but more like it's able to like come down horizontally and it's just able to like hover down straight away.
So what's difficult about that?
You might encounter like probably like hazards, and you might probably require like a flat surface as well, and probably human factors.
Sorry, probably the dust kickback was one of the issues that was talked about it. So the way that the thrusters are actually set up on this, they're at least 7 meters back. At least the main propulsion thrusters, when it's coming down, are at least 7 meters back from where the cockpit is. So that's a way that was preliminarily mitigated the risk of dust feedback, but obviously it's definitely a concern.
While we continue with the questions, would the next group set up their presentation?
Just add to that. I mean, it's not. I think it's important to note it's not like we're proposing some fundamentally new way of landing on the moon. It's just that almost the orientation of the astronauts is sort of in a sitting position, as the vehicle comes down, rather than standing up and landing, on its back. So we don't anticipate it's going to sort of pose a landing challenge that's fundamentally different from what's been going before. It's more like a human factors thing of how the vehicle is configured.
What I didn't understand, though, it looked like the front part of it, which was the pod where the astronauts were was also the ascent module, and it certainly was not clear, at least at the level of detail that you showed, how the ascent module is supposed to get away and go back into orbit.
we intend it to actually be a reusable vehicle, so but we didn't exactly study into like the detailed operations as to how the ascent module might eventually separate from the descent module. So we are still sort of exploring the ideas of whether the ascent module and the descent module should just live together if we want it to be like a fully functional, reusable spacecraft, or we might just follow the Apollo program again, where the descender module will provide the propulsion platform for the ascent module to go back, return to lunar orbit, and perform the lunar orbit rendezvous with the Orion spacecraft before performing a water landing back on Earth.
The lander concept is based on a study done by ULA, and they do have concepts both for vertical takeoff of the entire vehicle and also for separating the ascent module. I don't remember offhand what their sort of architecture was for getting the ascent module off the descent module, but it is in that ULA study.
Just a quick question about your landing site. I didn't fully understand it. So you're not landing at a permanently shadowed, permanently illuminated site, is that right? You're landing in the SPA, but not at the pole.
Yes, because we want to be able to see.
Right. So, yeah. So, but your power plan includes enough power to survive the 14-day lunar night?
Yes, we have enough power for the first mission, but we eventually want to have like power for sustained missions. As mentioned by Giuseppe, we plan to have at least like 800 antennas, and maybe in future missions we will not be turning to astronauts again. We might just be turning to purely robotic missions to deploy the remainder of the antennas, and for that we might need like a moon-based power supply.
Part of the sizing, I guess we don't have the slide up anymore, but part of the sizing for the power system included the batteries. I mean, that's actually almost all the mass because the solar panels weigh nothing compared to the batteries for lunar night.
Yeah, and basically throughout the whole project, we have been using a combination of existing technology and modifications to ideas so that it will be more viable in future. And I think she has a question.
Pass the microphone back. And John, we'll make John's the last question.
Since the setting up the astronomy is like the main purpose of your mission architecture, couldn't that be accomplished without astronauts? Like, couldn't you launch that, have them deploy themselves, and then that reduced a whole bunch of your costs, right? Because you're not looking at a whole lot of like human studies, or what it sounds like. Like, if that's your main goal, it seems like that'd be a big way to reduce costs, is just automate the whole thing.
Yeah, we did have that concern as well, but we felt that for the very first mission, at least with current expectations of what technology can achieve, we prefer to have astronauts up there as well so that we can like, perform any physical testing. And we are unsure as to how one antenna unit will actually perform on one of the landing sites on the moon. So if there are any like major errors or any like malfunctions of the equipment, we can have astronauts who will remedy the situation immediately. So as mentioned by Cameron, we have 4 astronauts, of which one pair will be on the LRV, who will be deploying the antennas out on the lunar surface, and the other 2 will remain on the Centaur vehicle to actually perform like checks. So the moment one antenna goes operational, the other 2 astronauts will be testing if you can actually receive data from the fringes of the solar system.
So that landing sequence, you're on the descent engine, and then you're in some translation mode after you shut the descent engine off, and you're using the smaller jets. That's providing enough thrust to. Have you thought through that whole sequence of sort of translating from?
Yeah. So obviously that's a concern. So. We took the bare bones of what the Centaur has been proposed. So for that vehicle, it has 24 kilonewton biprop thrusters on the side that allow for rotation and translational movement. But again, that transition, like the attitude, pretty much remains constant during descent, relatively constant. Like the RL-10 engines slow it down, and then that primary propulsion shuts down, and the 20, at least in this case, the 20 thrusters start activating, and each of them are gimbaled and can throttle at their own pace.
Good job.
All right, good afternoon, everyone. This is Team LURS. My name is Anthony Pang. I work on mission architecture and rover architecture.
I'm Caleb Whitlock, and I did GNC.
I'm Louis Boulanger, and I did mission architecture and rover architecture.
And I'm Jacob Ames, and I was responsible for operations.
And today we will give you a full overview of the LURS program with a full background and motivation on LURS, mission architecture, GNC, rover architecture, and operations, and we'll conclude with the significance of this mission. So, as you all very well know, from various talks from Maria Zuber and from Jim Head, that a manned presence on the moon would be very excellent for further understandings of geological science. However, as you have heard in the last 2 days of presentations, resupplying these astronauts is pretty costly given that you need food, water, oxygen, and at the very minimum, just getting to Leo costs $1,000. And as was noted before, the $1,000 is a pretty liberal guess by SpaceX on how much that would cost. So the good news, however, is that there have been reports of natural resources on the moon that could be used for these expeditions, including oxygen, which could be found in a regolith, particularly in a mineral called ilmenite, and water, which has been discovered at the poles by the Lunar Reconnaissance Orbiter and by Chandrayaan. So we know there's water, possibly. We know there's oxygen, but where? What's the concentration? Like for future habitation, or any long-term mission, we want to know exactly where in the polar regions we have water, how much ilmenite you actually have in the regolith for oxygen extraction, and you want a location for these missions where you have either direct line of sight to the Earth for communications, or having some sort of relay satellite for dark side communications. So we need to quantify these variables before we even send a man on the moon. We want to have the best informed decision, and using the most modern technologies, such as rovers, which have been clearly the best choice that NASA's done in the last 30-odd years on Mars. We want to take that sort of methodology, bring it to the moon as a precursor to an Apollo-type manned mission. So LURS, which is a lunar unmanned regolith extraction surveyor mission, we want to send unmanned remote-operated rovers to sites of importance in science. And in those locations, we want to, A, find the ilmenite concentration, B, try to find the water concentration, and C, do technology demonstration of key technologies that you need to ensure that you have these resources for astronauts. Let's think of these like as Apollo 2 through 6 before Apollo 7 onwards. So the location where we want to land, you probably heard of this location from multiple presentations, but Shackleton Crater near the South Pole is excellent location for both from a habitation perspective and for science missions, which we will illuminate in a moment. So as you have probably heard already, there's suspicions of water at Shackleton Crater. Of course, we don't know the concentration exactly, but that's what this mission's for. We also know the topology of Shackleton Crater. We know that it has a rim. We know it has areas where it's illuminated by sunlight 80 to 90% of the time, which is excellent for solar power. And we know that the rim itself has locations where it's not highly sloped, so you can send both manned and unmanned expeditions into the crater to do a lot of these missions. Last, as I mentioned, the criterion for success for a human habited mission or a long duration mission, having water source, possibly check. Access to solar flux, we have 80 to 90% of the time. There's direct line of sight to the Earth, and we also plan to add supplement with relay satellites, which we will cover in a few moments. And the mission is, of course, to find out how much ilmenite is there in the soil. So the scientific value, as you heard in presentations before, is proximity to the South Pole Aitken Basin, which is known as one of the deepest impact and oldest impact locations on the moon and in the solar system. The basin's over 12 kilometers deep. A lot of information about the interior of the moon can be discovered in this mission. Well, for subsequent manned missions there, once we found out how much resources you can extract. So the concept of operations for this mission, we will launch on the Falcon 9 rocket, get into orbit, get to the moon, and we will have a powered descent. We will go into a lot of detail with Caleb in a moment. Once we're there, we will collect soil samples and map out how much ilmenite you have, and using deep ground penetrating radar, find out how much water you have on a high resolution scale. And all the while, you'll be communicating with the Earth using the Deep Space Network. And moving on to guidance, navigation, control, this is Caleb.
All right, thank you, Tony. He described a brief overview of the mission architecture. I'll describe a little bit more detail about the exact guidance, navigation, and control strategy we'll use to actually get there. So one must recall that for the Apollo program, there are a few different modes considered. They considered lunar orbit rendezvous, Earth orbit rendezvous, and direct descent and ascent. For our mission, we chose right away that direct descent and ascent was the best strategy, since there was no return mission and there's no need to loft extra propellant or anything. This is just a one-shot mission. And the strategy has been demonstrated over and over again with the Surveyor probe. So we're going to use a very similar profile to Surveyor to actually accomplish this landing. The descent and landing itself is also very important because we need to ensure that we are able to actually get the entire rover to the surface for a soft landing. And our strategy is to use a landing platform that has the rover on top of it that will land on the moon, and then the rover will simply drive off of the platform. Third, for navigation in cislunar space, this will be accomplished in a similar manner to most other probes that go to the moon using the Deep Space Network for tracking, and it will be primarily autonomous. All right, so this is an SDK simulation we constructed of the mission from launch through lunar landing. This first segment shows the launch from Cape Canaveral aboard a Falcon 9 Heavy rocket, which is able to loft the necessary payload capacity to translunar injection. Approximately 5,400 kilograms is the capacity, and we're budgeted for about 5,000 kilograms. This is followed by a short coast segment to ensure we're in proper alignment, followed by a translunar injection maneuver of about 3.1 kilometers per second. And then we enter a coast in cislunar space. This coast happens for about 56 hours before we enter the proximity of the moon. And then we did this with the assistance of B-plane targeting and other techniques to find the proper, to get the proper alignment before we actually began the descent phase and the braking phase. So for the braking and descent, we coasted until we were relatively near the surface of the moon, about 27.8 kilometers. And at this point, we're traveling about 2.3 kilometers per second, which is very high velocity. So we initiate a braking maneuver using a solid rocket motor, much like the Surveyor missions, with a duration of 40 seconds on the burn. And that'll bring us down to about 8.6 kilometers altitude, at which point the solid motor will separate, and then small vernier engines will be used to perform the final braking and actually align for the descent and perform any corrections as required. And the landing strategy is much like was discussed in the last group, just using inertial measurement units and gyros within the platform itself, in addition to landing radar. And this landing will be primarily autonomous, and we'll be able to change landing location based on the topography that we encounter when we actually get there. This is a summary of the maneuvers that are performed. I won't go into this in detail because it's a little bit exhaustive, but this more or less explains that we can accomplish a mission within the mass budgets that we specify, and the strategy is not unreasonable at all, and is a fairly simple strategy, much like the Surveyor missions that's been accomplished many times, and we believe it's a suitable option for our mission. Next, I'll hand it over to Louis, who will discuss the architecture of the rover itself.
Okay, thank you, Caleb. So now that you know why we are going to the moon and how we are getting there, so I'm going to discuss rover architecture. It will not look like that. So the main subsystem I'm going to discuss are first the chassis and motor drive, then the mineral extraction and processing package, then the power generation and storage device, then the sensors, computers, and communications. So this is a preliminary mass budget for the LURES rover. So the breakdown is as follows. So you have 500 kilograms for the chassis and motor drive, 80 kilograms for mineral extraction and processing, 30 kilograms for sensors, 180 for power generation, 20 for computers, and 20 for comms. So it gives you a total of 830 kilograms. So this is a big rover, but this is realistic. This is about the same mass budget as a Curiosity mission. This is clearly something we can achieve within years. So first, the primary objective of the mission is to demonstrate oxygen extraction from regolith. Because lunar regolith is largely made of oxides, so you have a lot of oxygen, just available for you, but you have to extract it from the minerals. So several processes have been proposed by researchers to accomplish that. We choose to focus on the design that was made here at MIT Department of Materials Science with assistance from the Aerospace Corporation by Sirk and Professor Sadoway, which is very simple because it simply consists in direct electrolysis of molten lunar regolith, and you simply get your oxygen bubbles here at the anode. But of course, the problem is that it requires to melt the sample and heat it at 1600 C. So this is a high temperature, but this is with a 100-gram sample and 2 kilowatts of power, you can achieve this temperature within a few minutes. So 2 kilowatts is a lot now. So you are going to ask, where do we get this power from? This is the next part. So LURES will generate power from two sources. First, RTG for continuous power generation. So for design, we assumed that we would use GPHS RTG, which was proven and used on Galileo and Cassini spacecraft, for instance, which produces 300 watts of electricity. But NASA is currently developing the advanced Stirling radioisotope generator that would have a much better efficiency and power to mass ratio. And so given that we are a very power intensive mission, if this technology is ready for flight when we launch URS, we will probably switch to that technology. And then we will complement that with 5 square meters of high efficiency solar panels on an orientable mount to keep them perpendicular to sunlight. That will generate 1500 watts of power. And for flexibility and supplemental power, we will have batteries. So a very interesting addition to this power system that, as far as we know, has never been implemented on the spacecraft would be to be able to use the waste heat from RTG, because as you probably know, the efficiency of the conversion from heat to electricity in RTGs is terrible. It's like between 5 and 10%. But on this mission, the biggest power drain is precisely melting the regolith. So if we use current technology, we will convert heat to electricity with a terrible efficiency, and then we will convert this electricity back to heat, which doesn't look like a great idea. So the solution would be to transfer heat directly from the RTG core, which is at about 1000 degrees Celsius, to the processing cell at 1600 Celsius through a heat pump. And if your heat pump has a maximum thermodynamic efficiency, you can prove that this would reduce the amount of electrical power you need by a factor of 3, which would vastly improve the processing capabilities of URS. Then the power management will feature 2 very different modes, because in this mission, the rover will go both in the crater and on the rim of the crater. So you will have first a crater dark extraction CDE mode for operation within the crater, and then the solar powered supplement STS mode for operation on the rim of the crater. So in the CDE mode, your rover relies solely on RTG and batteries, so you have very limited power. You have a very limited power available, so you have to manage it tightly. So in this mode, we will stay focused on regolith collection and probing the ground for water with a ground-penetrating radar. Then, when you go back on the rim of Shackleton, which is almost permanently sunlit, you will have 1800 watts of electric power provided by solar panels and RTG, and with possible supplementation by the batteries. So, in this mode, you will do all the very power-intensive operation like ilmenite processing and oxygen extraction. And as I mentioned before, the load on the electric power supply system could be greatly reduced if we manage to use the RTG waste heat. Then I'm going to discuss the sensors. So further sensors, of course, will include multiple cameras, including infrared and low light cameras for operation within the crater. And then we will have, so it's something that Jim had talked about. He said he would love to have this experiment done on the moon, a ground-penetrating radar to look for water, because some scientists think that water ice, if it exists at the South Pole, could be buried beneath a layer of regolith. So you need something to look beyond the layer of regolith. So there is this interesting design. It's the Wisdom radar that was designed for use on the ExoMars rover. Which is very compact, only 1.4 kilograms and 15 centimeters in the biggest dimension. But the penetration is somehow limited. It's only a few meters. So as the URS rover is much bigger than the ExoMars rover, we will probably want to scale up this device to have a better cartography of the lunar ground. And now I'm going to let Jacob present you.
Thank you, Louis. So here's an outline of operations which I was responsible for, and we're going to start out with authority and the evaluation of mission status, which is going to be continuous throughout the mission operation. Constructed a link budget, and we'll give you an idea of communication strategies, as well as rover controller training and situation awareness with the heads-up display. So authority and evaluation of mission status. Naturally, this is critical to monitor all the major subsystems throughout the mission simultaneously. And because of that, we want to assign an individual to monitor each subsystem throughout the mission and each of them will give updates to the lure's equivalent of the Capcom from Apollo missions. And so the rover controller will be responsible for executing the decisions made by the Capcom, and this hierarchy is similar to what was seen in the Apollo missions. For link budget and communications, we had to make a few very important assumptions. Perhaps the most important of which is that the relay satellite has more than adequate power for transmission, and that it's also equipped with a NASA inflatable SRS membrane reflector for sending and receiving. Now, this isn't a technology that exists currently, but it's in development and expected to be available before the implementation of the lure's mission. So we assumed an Earth-Moon maximum distance of 405,500 kilometers and a rover-to-satellite maximum distance of 15,000 kilometers, and this is at the apogee of Manoia orbit. So we also selected Ka band for all data transmissions at 34.7 gigahertz. That was specifically because of the high bandwidth capability of that frequency. Additionally, an 8.17 times 10 to the negative third meter uplink wavelength and a 9.36 times 10 to the negative third meter downlink wavelength. So this is a diagram of the communications. You can see here we're operating from the Deep Space Network on Earth, transmitting signals to a relay satellite in a Manoia orbit around the moon, and then transmitting these signals to the rover at the Shackleton Crater. So the power requirement calculations from the Deep Space Network antenna to the relay satellite. We first calculated free space loss, and that is 32.45 plus 20 times the log of the distance from the DSN to the relay satellite, plus 20 times the log of the frequency in megahertz, and that resulted in 235.42 decibels. The receiver gain is then calculated through the formula shown here using the signal wavelength, and that's calculated at 65 decibels. We assumed a link margin of 5 decibels and calculated the power requirement to 43.42 decibels, which is equivalent to 21.98 watts of power required to transmit the signal from the Deep Space Network to the relay satellite. And then using the same strategy, we calculated the power required from the rover antenna to the satellite, and I won't reiterate how the formulas work, but we used a link margin of 10 decibels in this case, resulting in 20.97 decibels, or the equivalent of 0.125 watts. And that's what's required on board the rover in order to transmit signals to the relay satellite. Now the rover controller training. This is an important part too, because this is our human factor in the loop. And we're selecting 2 controllers based on a candidate pool and based on remote control and robotics experience. They'll be trained for 2 months on mission objectives and the lunar topography because we want them to be familiar with the terrain. And they'll be trained for 6 months in a simulator executing mock missions, and then primary and backup controllers will be assigned after a skills assessment, after which the weak skills will be honed for 2 more months before execution of the mission. And the total training time, depending on the learning curve and if the controllers are on an accelerated schedule, will be between 9 and 12 months. And this is just a flow diagram of the controller training along with the timeline. So we have evaluation and selection of candidates, basic mission training, simulation training, and then a competency assessment, which is followed by primary and backup controller assignments, additional simulation training, and then an execution of the mission. Another very important factor is situation awareness. That was just as important in this mission as it was in Apollo. And since we're having live video footage from the lunar surface and feedback from physical sensors and also the Wisdom sensor, these are going to be displayed on a heads-up display for the rover controller to interpret and make appropriate decisions. So we are employing the situational awareness global assessment technique. I'm sure some of you are familiar with that. SAGET is employed in aviation, but we're adapting that for our purposes as well, and along with other methods. And we're going to evaluate the heads-up display to ensure that it's not distracting and that it allows the rover controller to use it to its maximum potential. And so throughout the training of the rover controller, changes and evaluation of the heads-up display can be made in order to make it work most effectively. And then, finally, we're going to look at the rover logic and data transmission. So commands are sent through the DSN to the CPU of the rover, and all the subsystems are controlled by the commands that are sent through this computer. So they're distributed to the subsystems. The subsystems will then return feedback to the computer, which is routed back to the heads-up display so that it can be perceived by the rover controller. So this is just the layout of that. We have the rover sending commands to the computer distributing those commands to the appropriate subsystem, and then the subsystems returning feedback to the rover controller. And so to conclude, I'm going to give it back to Anthony.
Okay, so in conclusion, we have a design LURS which would fulfill all of these pre-Apollo-esque missions with a technology demonstration of ways of extracting these resources, means of actually mapping out and quantifying how much of these resources we have on the moon at Shackleton Crater, which is a site of major scientific significance. And from many lessons learned from Apollo, including contracting out the science mission to MIT, we have high confidence that the LURS mission would succeed if accepted.
On your trajectory, using that 3-day, surveyor modeled approach, did you consider the alternatives like the Grail 90-day trajectory, which actually results in a much lower delta V required and maybe more efficient? You have a nuclear powered reactor that could, 90 days doesn't really matter in terms of the transit time to the surface.
We just considered that since the launcher would be low cost anyways, it wouldn't really, we didn't evaluate this in detail, but it's just simpler to go with a direct launch and direct descent, and the mission could be accomplished in a more timely manner, but it certainly could be accomplished, enter a weak stability boundary transfer, and then the delta V requirement would be lower, which can increase payload capacity, but since we're already within our margins that we have, it wouldn't really be necessary.
The first is a bit of a nit, but people make this mistake all the time, and you talked about the dark side of the moon. It's not the dark side of the moon, it's the far side of the moon. Right. Okay, so we'll get over that. Given the current, we looked at Curiosity as sort of as good accuracy landing as has been demonstrated possible for a robotic spacecraft. But you're trying to land near the rim of Shackleton Crater. What is your required landing accuracy, and how does that compare to what currently we can do?
Actually, do we have the... So we have the... Actually, I'm going to show you the spot on Shackleton Rim where we would like to land. So okay, we will arrive here. I think the required So actually, the best spot probably would be on this ridge here, because it has been demonstrated that this location is for sure sunlit, like for 80–90% of the time. So so we have, I think we have a landing spot of about maybe 10 square kilometers landing area where we could land. I must say I don't know how it compares with the accuracy that was achieved on Curiosity, for instance.
Just a little.
This region here.
I'm a little confused about the scale. On the right, that's a vertical scale?
Yeah, this is
okay.
This is vertical scale for depth.
That was confusing. Okay. And the other thing, unless I missed it, you didn't talk much about the technology required to operate down in the crater where it's really, really cold.
Yeah, we would need to heat the subsystem with, from the RTG or, But I think it has already been done on several missions. No, I mean not going in the crater, but like heating, maintaining the heat of subsystem. No, yeah, I agree. It has never been done to go back to go down in the crater.
This is really pushing technology to operate at 40 degrees Kelvin.
Yeah, so one of your major goals is to get titanium from the surface. So have you considered what the abundance of titanium is in this crater? Because, I mean, most of the titanium on the moon is in Mare basalts, and very, very little of it is in, tend to be in highland sites.
It's not actually titanium, but ilmenite, which is an oxide that is especially rich in oxygen, which is our...
I guess what I meant to say ilmenite, apologies. Okay. So that the ilmenite abundance in highlands rocks is extremely low. It can be essentially 0%. The lithologies that it's really rich in are certain types of mare soils. So I'm just wondering if, have you estimated why do you think this site would be rich in ilmenite, given that it's basically a highland site?
Well, actually, that's our mission. We want to find out how much ilmenite there is. We don't actually know. We know the Hubble Space Telescope in 2005 performed some experiments to look for locations of ilmenite, but they're extremely limited, and I don't think they've performed them at the poles either. So we want to find out how much ilmenite there is, and Sadoway postulates that other forms of regolith, less rich in oxides, could also be used. So this could help us find out how much ilmenite there is and alternative regolith fuel that we could use for oxygen extraction.
I had thought from what I've read about Sadoway's work, I mean, he was actually originally looking at producing iron, raw iron, by electrolysis, and he kept getting bothered because they were producing all this oxygen as a waste product, which he had to get rid of somehow.
Yeah.
But I think there may be some fundamental confusion, because what Ben says is right about the ilmenite. I mean, originally for oxygen production, we were looking at ilmenite, but using a different process. It was a hydrogen replacement, and that was going to be in the Mare regions. I mean, the interest of Shackleton Crater, I don't think is in the presence of ilmenite. It's the potential presence of actual water ice. Mm-hmm. And if you find the water ice, well, then you can produce oxygen by electrolysis of water. So there's a little bit of confusion there, I think.
I was just going to question, one of your main themes, I think, is you have a lower cost mission than a lot of the others propose. It's robotic, it's not human, single launcher, using seems like a lot of more existing technology, but there's no cost analysis. That would seem to be like one of your main advantages. Why is that?
We didn't do a detailed cost analysis, but I think this mission would allow to reduce the risk of a possible return of man on the moon, so that you don't have to expose needlessly the life of astronauts to map out resources. And I mean, if we decide to send men back on the moon, I think we can afford such a mission, but yeah, we haven't conducted a detailed cost analysis of this project.
Questions from the class? Yes.
Okay, so a little question about your CONOPS. So you mentioned that you're going to be using a satellite that's not going to have 100% communications with your rovers. There will be outages. Is the plan just that the rover is inoperative during those times, waiting for human-in-the-loop control?
Well, yeah. I mean, as far as I remember, I know you did a calculation on the amount of time that was that we were actually going to be in communication with the rover. Was that on the order of 23 hours?
No, it was like 18 or something.
18. Okay, so we're still looking at 3/4 of a day that's going to be available for communication. So as far as those outages, it's just going to be a time where we won't be operating the rover, and we don't expect to be in any sort of hostile environments. I don't imagine that being a problem. That I don't have any estimates on.
If you put two satellites, you can have much more permanent coverage.
And the rover itself is semi-autonomous. There's a lot of operations that are built in array. Like the extraction process is autonomous. The processing process is pretty autonomous. So
you just say go and it does it.
Yeah.
Okay. All right. Thank you. Great.
we're Team Orpheus. I'm Megan. This is Brandon, Tom, Vishnu, and Austin. All right, so Orpheus stands for Operational Research Platform for Human Exploration of Unknown Sectors. It's also the name of a son of Apollo. So what we're going to go through today is the motivation, the station, lunar lander, science objectives, transportation, and I guess it's some costs. So motivation. So before we get into what we're doing, overarching objective, what are we trying to accomplish when we sat down to talk about what we wanted to propose? We want to create a useful, extensible lunar mission that uses both manned and unmanned assets. So useful, we want to focus on how can we best accomplish scientific objectives for the moon. Extensible, how can we create something that's not just going to be a one-time shot for the moon, but we can extend it to Mars and future deep space missions. Manned, we want to inspire a new generation. We want to get manned space presence going again. And then unmanned, we also know that there's a lot of good science that can be done by robotics, and we want to integrate that into our architecture. So the main idea behind our project is a station at Earth, Moon, Lagrange Point 2. So I don't need to belabor this point. You have heard a lot about L2 so far. This is the idea of a relay satellite, but what we're proposing is actually putting a station in a halo orbit around L2. And the big idea behind this is that you could launch to any point on the moon's surface. You have equal access from the station, and you have unlimited launch windows. So you can get to any point, do science missions there. It also allows for a D-space node for experiments. And then again, rather than having a lunar outpost on the surface of the moon where you can only get within that region, you can go to any point on the moon when you have a station here. We looked at some of the other options, but we decided that with our objectives, trying to get the largest return from science, this would be our best option. So some of our proposed accomplishments, for science, we could explore multiple sites. We'll do lunar geology, in situ resource utilization, and radio astronomy, and we'll talk more about that. And then, again, with extensibility, what we're essentially proposing here is a Gemini program for Mars. So we're going to study a lot of the things that you would have to study for Mars missions, long-term exposure in humans, partial gravity concerns, a lot of the decisions that you have to make in engineering that you would consider being outside of low Earth orbit, human-robotic interactions, and we're going to take a look at the communications lag, which is going to be critical in any sort of long-term mission far away from Earth. So some of the hardware that we're going to need to be able to accomplish this is a station, obviously, the lunar lander, rovers that we're going to use to do the science, and then we're proposing solar electric propulsion vehicles. So with that, we'll get into the station with Brandon.
Let's see if I can handle the microphone and the remote control at the same time here. So when we're talking about putting a station at Earth, Moon, L2, there's a core architecture considerations which actually drive this particular selection. The first one is just to simplify the sorties and excursions to the lunar surface. We want to reduce the mass you have to bring up from Earth every time you do a mission. And basically the idea is you're paying for an upfront investment of architecture so that your future long-term costs are actually reduced. And we want this to be an extensible architecture that supports lunar operations, but also other operations in the Earth-Moon system, and then ultimately Mars exploration. We want to maximize our scientific output by being able to go all over the moon. And we also want to minimize risk to astronauts. And one of the virtues of this station at L2 is you have a free aboard option for any operations that you do on the surface. So the logic behind this particular design is actually goes back to the Apollo era, specifically with Skylab. And the idea is you have an inexpensive launch vehicle-derived space station, which is actually not particularly limited in its mass or its volume. And you can launch it fully provisioned, and it has a large working volume, and it's compatible with your existing vehicles. And this turns out to be a much less complex and a much less expensive model than the ISS model, which we've seen more recently. So building off that Skylab design, we're actually going to start with an SLS vehicle here. And we've actually sized our station so that it will fit on the Block 1 vehicle, which is a 70 megaton, metric ton, apologies. 70 metric ton. So it's a 70 metric ton station. And what that means is that you can use the Block 1 Heritage core stage and boosters. And we're actually going to take advantage of the full volumetric capacity of the Block 2. So we're going to use the aerodynamic shell of Block 2, but instead of having the second stage and a normal payload, we're going to actually just put the entire station on top of that. And that's very similar to Apollo, where they took the third stage and turned it into a station. And we're going to launch this thing to LEO. It's going to deploy on orbit, and we're going to use a solar electric propulsion tug to actually transition it to the operational site. And this is sort of our detailed station design, and I'm going to talk to you about the 3 basic components of this. And so the first is, I'm just going to cut it away here a little bit. The first part here is actually a rigid module, and this is direct Skylab derived. We're taking the fuel tank from the SLS design that already exists, and this is actually what that looks like. As you can see kind of the scale here. And we're going to outfit it and put all of our consumables and our equipment and everything that we're interested in. This is actually what that looked like on Skylab. And it's really easy to do. You already have a structure that supports your vehicle. It's structurally stable. It has huge safety margins, and you can put everything you want in it. Our second part of the module is actually a pair of counter-rotating toroidal modules, and the idea here is that these are inflatable, deployable rings, and they'll counter-rotate. They'll give you partial gravity. You can either simulate lunar or Martian gravity conditions, and the idea is to start testing, well, what does that mean? Does this actually provide us the ability to reduce the negative effects of deep space habitation on human crews? And then the third stage is actually a combination sun shield and consumables depot. And the idea is we're actually going to take the payload fairing that we use to launch the vehicle in the first place. We're going to permanently connect it to the station architecture and make it the deployable, almost like an umbrella. It'll deploy out, and attached to that will actually be your solar array and a sun shield. And the idea here is reduce consumables boil off, maintain a constant thermal architecture for the station itself, so you don't have this constant heating and cooling cycle that you get on ISS. This is going to reduce our maintenance costs for the entire station. And because the station is always in shade, you actually don't have as much radiation damage to surface materials. And so this is sort of the overall thing. Again, single launch station. We're going to minimize the maintenance costs, and we're actually going to provide a lot, because we're pre-positioning all these resources, we're going to actually really give some advantage to astronauts from a health and safety perspective. And I'm going to hand this off now so we can talk about the actual lunar landing architecture.
Okay, so I'm Tom, and I'm going to talk about the lunar lander. So we want our lander to go directly between our station and the lunar surface, and then back again. And we want to carry 3 astronauts with provisions, plus 500 kilograms of cargo delivery for some scientific experiments and small rovers, and we want to be able to return 100 kilograms of samples. And we want to be able to maximize the reusability of the lander, because we have the station, we can dock it there, we can refuel it, and hopefully use some of it again. Now, there are a lot of different lander designs to choose from. In fact, there are over 100 when you look at the literature, mostly because of a lot of proposals for the recent Constellation program. So now we're going to think about some things we had in mind when looking at good lander designs for our mission. So one thing is propellant selection. I'm just going to compare as an example the Apollo LEM and the Altair. Now, Apollo had an Aerosine descent stage, which is a hydrogen-based propellant. But with Altair, they improved on that significantly by using a LOX hydrogen descent stage with a much higher specific impulse. But then if you think about the ascent stage, again, they used Aerosine for Apollo because of its simplicity. And by the time Altair came along, they'd improved upon the specific impulse by a whole 8 seconds. So we'd like to try and do a little bit better than that. And one thing that's been under consideration recently is using LOX and methane instead. So the reason that LOX hydrogen can't be used for the ascent stage is it's not storable on the surface. Some of it will start to boil off if you leave it there for a few days. It's okay to do that on the descent stage because that's going to happen fairly quickly near the beginning of the mission before much of it has had time to boil off. So LOX methane has a decent improvement on specific impulse over hydrazine, but is it storable? Well, at first glance, it might seem that it's not, because it also has to be stored at cryogenic temperatures. So again, you might think that you would have significant boil-off if you left it on the surface for the duration of a 14-day sortie. But then if you compare it to hydrogen, it actually is a lot better. It boils at a much higher temperature than hydrogen. If you compare it to the hydrazine-based propellant, well, it doesn't look so good because that doesn't boil until a high temperature. But you also have to consider the freezing temperature, and hydrazine actually freezes at a high temperature. In fact, you have to heat it while it's on the lunar surface to prevent it from freezing. So you actually save a whole kilowatt of power by using LOX methane instead of hydrazine, even though hydrazine doesn't need to be frozen. So that was our propellant. Now, general characteristics of the descent stage, most of them are determined by the requirements of the actual final stage of the landing, like high maneuverability, a high throttle range on the descent engine, and being able to withstand the loads of landing. I mean, of course, we want the high specific impulse, and it'll end up being discarded on every mission, but the key characteristics are really those final moments. But with the high specific impulse in mind, it's worth bearing in both comparing this descent stage to other rockets that have high specific impulse engines, and the only ones that do are upper stages of rockets. Now, these are the only current purpose for which LOX hydrogen engines are used. So we have like the Delta IV and Ariane 5 upper stages as examples. Now, obviously, these can't land, but they do provide us with the high specific impulse, and they also get discarded on every mission anyway. So if you actually don't land all the way with your descent stage, you drop your descent stage before you hit the ground, you can get away with using an upper stage as your descent stage without any further work required. So we wanted to choose a lander design that does this. And the design that we settled on is this one by Boeing. It attaches, here you can see a Delta IV upper stage, but you could use an Ariane 5 one as well, and that gets dropped about 4 kilometers above the surface before the engine would have to throttle down very much. And then the lander itself takes care of the remaining 500 meters per second of Delta V. And let's see, this isn't working. Oh, it is now. Okay, so here you can see the stage in the purple being dropped and hitting the ground while the lander carries on to a controlled landing a little bit further away. And this lander can be completely reused. It uses LOX methane for its propellant, and it can travel between EML2 and the moon in around 3 days. And just in case of any damage to the lander, we plan to have a backup lander docked at the station, which can come down to rescue the astronauts. So with that, Vishnu is going to talk about the science objectives on the surface.
All right, thanks. My name is Vishnu. I want to talk about the science objectives for this campaign. So our key science objectives that we followed for this project are derived from the Constellation study. It was published in 2005. Basically to conduct three key objectives. First one, to study planetary processes. So that's using the moon as a natural laboratory, surveying geological sample collection excavation, followed by ISRU. And of course, this ISRU extends to Mars as well. And then finally, we, just like the first group that talked today, we want to construct radio telescopes in a networked array on the far side of the moon. So site prioritization. So we derived this priority of sites because obviously we are a sortie-style campaign. We can go to multiple sites. And because our station is at EML2, we can actually visit all top 10 sites on the moon, thus allowing us to spend few days on each site rather than setting up a base on one single site. So our first objective, lunar geology, how do we do it? Well, the first way you do it is with astronauts. So what we propose for crew transportation is an upgrade to the LRV. It's called the DMLRV. It was proposed by JPL. It's an upgrade over the Apollo LRV in two main ways. The first is, of course, it has more payload capability. But one of the key ways it is an upgrade is this cargo module that you can attach. And this cargo module expands its cargo capabilities. It's modular, so you can change out cargo modules, so different science equipment at different times for different sorties. And then you can also, it has MMRTGs right on the cargo module so that you can teleoperate this rover once your astronauts have left the surface. So you can hypothetically move this rover to another location on the moon and set up for another sortie. So the tools themselves that the astronauts are using for lunar geology, we want to just use an upgraded LSEP package, which includes seismometer experiments, digging tools, magnetometers, and solar wind measurements. One other thing that kind of drove home for me was Dave Scott's comment that he wants to try to make the astronauts' time more productive. So one way we handled that was using the K-10 rover. It's a rover proposed by NASA Ames, and it's actually been tested fairly well. It's considered the astronaut's assistant. Basically, it carries 15 kilograms of payload, not much, but it has an HDR camera, which allows a station-based operator or a ground-based operator to do mundane activities such as inspections of vehicles, or it can also be outfitted with a ground-penetrating radar. So potentially, this K-10 could be teleoperated from the ground or from the station, and could survey the area. And then, when astronauts are ready to do an EVA, they'll know exactly where to go. So in situ resource. Oh, sorry. The in-situ resource utilization is using the Resolve package. That's also another project that NASA is currently working on. It's handled by JSC and KSC. It's a 100-kilogram package that right now is outfitted on this rover called Artemis. But and just like the other groups that I've talked about, the key elements that they're trying to refine are volatiles, hydrogen, oxygen, and water. As an option, it is available as a package on the Scarab rover, which comes to my next rover, which is the Scarab. Now, Scarab is its own unique rover. It's a 280-kilogram, completely teleoperated rover. It is designed by Carnegie Mellon, and it's specifically it's advantageous to use in the polar regions where there's no sunlight. It uses MMRTGs for power. It also can traverse slopes of up to 60 degrees, so the deep crater walls are not a problem for it. And it has a laser navigation camera, so navigation system, so it can navigate and map out terrain even in the lunar night. So finally, our third objective, which is radio astronomy, and I realize that these numbers are not quite the same compared to the team that went today. But the far side of the moon was one of the most radio quiet areas of the solar system. And one of the big challenges with putting a radio astronomy network on the Earth is that the Earth's ionosphere blocks out wavelengths that are more than 30 meters. So if we can somehow shield the radio astronomy array from the ionosphere, put it on the moon, we can then be able to look at much farther regions of the universe, up to 1,000-meter wavelength detection. And in this case, we are doing all our computer processing not on the surface, but on the station. So right now, the antenna itself is about 1 kilogram, and I realize the numbers are different for the other group. But with the processing tools, at least this paper said it was about 20 kilograms. And so now I'm going to hand off to Austin for the transportation architecture.
All right. So now we've talked about all the stuff we're going to have. Now let's talk about how to move it around. So one of the main things that we mentioned was that we were going to use solar electric propulsion for moving cargo from low Earth orbit to our EML2 station. The engine we selected for that is a Vasimir engine, which is in development, prototyping, and testing right now, so it's actually kind of real hardware. And so with a low thrust engine, the kind of orbit that you end up using is a spiral orbit, which, although it has a much higher delta V cost, the fuel that you actually need for it is significantly lower than an impulsive chemical thruster because the specific impulse is so much higher. In this case, we believe we're going to have a specific impulse of 5,000 seconds. However, that comes at the penalty of a very long transfer time, which in this case is going to be on the order of 4 to 12 months, depending on how heavy it is, how heavy the cargo you're pushing is. And the return trip for just the tug itself is about a month and a half. However, you don't want to send your crews on a 12-month journey to EML2 because that would involve them spending a long time in radiation-dangerous environments and they'd get bored. So we're proposing for the crew transportation to use a more conventional architecture. There's this 3-impulse transfer, which was actually proposed in the 1970s, that takes you from low Earth orbit to EML2 in 8 days. So for the actual hardware, we're proposing using the Orion MPCV and service module, which are already being designed, an Earth departure stage, which is essentially a scaled-up Delta or Centaur area on upper stage, about 50% bigger. Okay, so what does a mission using this architecture actually look like? So first, this is going to be what we call our steady state diagram, which assumes the station and the space tugs are already positioned in space, and we've already launched a lander to our station. So this is a year in the life of our mission, but not year one. Okay. So, as I mentioned, we start out with the lander at the station and a space tug in low Earth orbit, pre-positioned. Then you use 2 heavy launch vehicles, such as a Delta IV Heavy, to launch your lunar descent stage, your lander fuel, and the surface supplies that you'll need for each mission. These rendezvous with the space tug in low Earth orbit and are propelled on a trip of about 8 months to the EML2 station. At the end of this journey, a Falcon Heavy is launched carrying the command and service module and an Earth departure stage, which are impulsively boosted to EML2 via the transfer I talked about. Once all that's at the station, it all gets put together into the lander stack that Tom described and performs descent to the lunar surface. As he mentioned, the lunar descent stage is jettisoned about 4 kilometers above the surface, and the lunar lander actually performs the final landing. After a 14-day surface mission, which accomplishes the science that Vishnu mentioned, they get back in their lunar lander and return the lander to EML2. During this time, the solar tug has been slowly turning its way back to low Earth orbit. Once that tug is there, or at any time before that tug gets there, you launch another set of hardware for a lander mission. It rendezvous with the tug, and the tug, again, takes it on a 6 to 8 month journey back to EML2. The lander, because it's already at EML2, is still there and ready for another mission. The tug, as before, makes its way back to low Earth orbit. The crew performs an entire additional surface mission, just like the one I talked about earlier. And then at the end of this, the crew gets back in the command and service module and does an atmospheric reentry very similar to Apollo with a splashdown. And you repeat this for as many years as you want to pay for it. Okay. And the really nice thing is, like I said, it's steady state, so you have a space tug coming in on the left, exiting on the right, still there. Same with the lander. Okay, so now what does this look like for doing a campaign? So really, you need to be able to justify a mission like this. It has to be better than starting from the ground every time like they did in Apollo. So just from a mass budgeting standpoint, we've got about 190 megatons of upfront costs for the station, the landers. Right, we're close. Okay, then the resupply is 40 megatons per year, crew transfer 50 megatons per year, and the landing hardware itself is only 40 megatons per landing, with that number being variable, and compared to 120 megatons per landing for a sortie. So the main takeaway from this is that this architecture is most efficient if you're going to do a lot of landings rapidly per year. And that's what this plot shows, with each contour being more landings per year. And with that, I'll turn it back over to Megan for cost and wrap up. Oop, that's the wrong one. Good luck.
All right, and real quick, just some assumptions before we jump into the costs. You can read those, so I won't repeat them. And then just a quick look at what NASA's budgets look like. They had about $2.9 billion for exploration, and then about 5.1 for space operations for fiscal year 2012. So jumping into our estimated costs, we estimated about $4 billion for the station, about $4.7 billion for the lander, most of that in development costs, about $1 billion for science per year, about $5.5 billion for the space tugs, again, a lot of that in development, transportation about $2 billion for the initial launch costs, operations about $3 billion per year, that's based on ISS, and that includes recurring costs, which totals us around $7.2 billion with about $4 billion per year. And with this disclaimer here that we did our best to find cost estimates based on sources and based on studies actually done, but we wanted to give a sense of feasibility. These aren't actual, we're not hard numbered costs. Finally, the takeaways, we have a sortie-style mission architecture, and then back to those 4 adjectives I used at the beginning, we wanted this to be useful, so we can do good science, extensible, so we can extend this to Mars, manned, and then unmanned as well using robotic technologies. Our design extrapolates existing technologies, so everything we talked about exists in some form, and we're just talking about extrapolating it. And then a unique part of our mission is that we're combining it in this way. And finally, it's a multi-year implementation. You got a sense for what one of the years looked like with Austin's, but there's the initial startup where we launch the station, get the landers ready, and then we start sending up the crew and then start doing the landings. So with that, questions?
So, cryogenic fuel for your lander. You pointed out correctly that you don't want to use it for taking off from the moon because it's hard to keep it for a long time because of boil off. And yet, you're going to launch it and use electric propulsion, taking 6 to 8 months to get to the moon. So you haven't solved the boil off problem, it seems to me. You're right in the thick of it.
Actually, we just launch extra fuel, so the boil-off is accounted for on the transfer. There's a study that estimates about the boil-off rate that you'd see for a reasonably shielded fuel tank, basically, and they estimate about 1% per month is what you'd get from a, designed but not over-designed for thermal management.
So in that case, why can't you use it for your ascent vehicle since you're only on the ground for 2 weeks?
Because the thermal environment on the ground is a lot less shieldable. There's a lot more sources of heat on the surface as compared to in space where you have a lot more control of it.
So I was wondering if you kind of compared this L2 architecture to a lunar orbit architecture? What are the real advantages? How much would you actually gain in mass efficiency, or is that kind of a stretch to be in L2 as the core part of this?
We didn't do an explicit complete architecture study doing the same thing at low lunar orbit, but the main disadvantage there is that you end up incurring a lot of plane changes, and that's either going to do one of two things. It's either going to drive your mass up by a lot, or it's going to limit your launch windows also significantly. And the fuel benefit of putting a station there is really, it's not, the delta V that it costs you to get to EML2 is actually less than it costs you to get to LLO. So there's not that we explicitly looked at it, but all of those reasons are a reason not to do one in low lunar orbit, plus the fact that low lunar orbits are also unstable and require a lot more station keeping than you would see at EML2. So it's just a host of negatives and not a ton of positives.
No, just to add to that, the abort considerations were also pretty key for us. We wanted to make sure the astronauts always have the ability to get back to the station if there's a problem on the surface, and also that the station can get to them if they actually physically can't leave. And so the nice thing about our architecture is you always have the ability to land whenever you want. You always have the ability to leave whenever you want. There's always somebody who can come and get you if you have a problem, and you can always go back to Earth if everything goes crazy.
And actually, Austin and Brandon did a good job of summarizing it. We briefly touch on it in the report, but for the same reasons, and just kind of harkening back to our objectives. Our big objective was scientific return, like our very first one. And so like Austin said, you can really get to every point from EML2, whereas if you pick an orbit, you really limit where you can go. And then, like Austin said, you have a lot more delta V considerations. So those are all the reasons.
Just to add another one, if you want to go somewhere else that's not the moon, if you put a station at EML2, you can actually use it as a staging place for going to Mars or any other place in the Earth-Moon system. Okay.
Maybe just a comment, not a question, but I thought your cost analysis was the most realistic of any of the ones that were presented. First, at least it's in the tens of billions,
yeah,
which is probably more realistic than the others.
I'll open it up to you.
Just one comment. Oh, okay, so Orpheus was the son of Apollo, but this is really the son of Skylab, huh? Right. So, what did you learn from using the tank as a Skylab vessel, and what is it that you found there? What are the positive and the negatives from that experience?
So, actually, one of the interesting things is, as we were looking at this, we actually discovered that NASA's been looking at this as well, and so I put in our backup slides. So this is actually the proposal that NASA's using, and they're just using a hydrogen tank. The key thing here is like half the cost of building a space station is figuring out how to keep the air in it. And the nice thing about a tank is that it's already designed to keep things in at much higher pressures than you would ever use for people. And so, it's already structurally rigid. It's a pressure vessel, and it actually weighs less, and it's less dynamic loading on the tank to put people and equipment in it than it is to fill it with hydrogen or oxygen or whatever it was you were intending to put in it. And so, because like the biggest challenge of building your space station is already done for you, and like this will come straight off the assembly lines they're already using for SLS, the outfitting is cheap. And so you save just an immense amount over what it would cost to do this any other way. With ISS, for every module that they built, they had to design an entire module architecture for it, and then they had to outfit it and everything like that, and they were very limited in their volume and their dimensions because of the space shuttle. This shows you the cross-sectional diameter here. This tank by itself is over 50% of the entire International Space Station. Our entire Orpheus space station is almost twice the in volume of the International Space Station. So you have a lot of working area, and you can do some pretty incredible things with this. And one of the other things I wanted to add is, this part here is really cheap, and this is exactly like Skylab. This would cost about $800 million to $1 billion to do. The biggest part of expense of our station is those rotating modules. And we wanted to do that because we thought gravity was going to be an interesting thing to explore. But if you wanted to risk reduce, take the inflatable modules out, and now you have a much cheaper station. It still accomplishes most of the objectives you wanted to accomplish for the lunar landing architecture, and you have sort of an optional flexibility there that you can either increase the capacity or not.
So let's see, your rotating inflatable was 16 meters in diameter, is that right?
Yes.
8 meters in radius. How many RPMs were you spinning it?
We were going to spin it about, I think it worked out to about 4 RPM. So it's significant, but it's not crazy. And actually, the previous proposals that NASA's done have used a much smaller radius toroid, and they're spinning at more like 8 or 10. And they seem to think that that was okay. So I don't actually. That's for partial G. I think we were doing Mars.
That does give you one G. Okay, questions?
Can I see the previous chart that you had on? It looks like a cost chart.
Oh, yeah. Oh, so this is just the idea here of this cost chart is just to show, and this is adjusted for $2010. Most projects you can get a big surge early in the campaign, but the thing that bites you is if you have a long, high recurring cost. And so the idea is, all right, you pay up front, and then and you pay up front in each of these. And I don't think you can see my laser pointer anymore, but if you can pay up front for the thing and then not spend so much later on, you still leave flexibility in the budget for other operations that you want to do. And so we're paying up front for the station and for the tugs and everything else, but then our recurring costs are actually much lower than you would have for a continued sortie from Earth strategy.
Okay, I'm not too sure if you have already answered this question, but I want to ask about payload sizing and weight or mass. So I understand that the payload capacity of the SLS that you're using is about 1104 meter cubes. So what are the approximate dimensions for the space station that you are designing?
So I'm just going to go back to a picture of the station. So we're using the same payload diameter. Can you? Yeah, I'm sure there's a more efficient way to do this. Thank you. There we go. So this diameter here, I'm out of laser, aren't I? Yeah. This diameter here, this is 8.5 meters. This is exactly the same as the SLS.
Yep.
And this is about 40 meters here. And we actually have a volumetric ability to expand. We can expand this out to 53 without getting any bigger than SLS is already intended to be.
Yeah.
So,
because that's sort of my concern. So are you going to redesign the payload section? Because right now it's about 1100 meter cubes for the payload section on the SLS. So if you guys have a length of 40 meters, it's going to exceed 1100.
So this part here is basically the equivalent of the SLS upper stage.
Okay.
And then this is the payload fairing. And so this is actually this is the exact same payload fairing they want to use. All we're doing is instead of discarding it, we're using it as a structural element.
Okay.
Yeah. But it's common. Is a common. The actual fairing is a common with the Block 1.
When is the first lander launched? One of that architecture. The architecture slide I thought showed the lander kind of just appears. How does that?
Yeah.
How does the lander get there?
The architecture was sort of like the steady state operations. There's also a startup sort of operations. The first thing that you launch is one SLS, which has this station and one tug, and that takes over a year to get to the EML2 point. After that, you launch 2 more tugs and your 2 landers, and then they go to the EML2 point, and then you start their Falcon Heavies. So
one SLS to launch the module,
and then two
Falcon
Heavies, which have a lander. So I gotta traverse the entire presentation again. All right, here we are. Okay, so the startup launch, what it is there's a Falcon Heavy that does everything these 2 vehicles do and that guy. So it's basically it's not that much more expensive really to launch another lander because the landers are only 5 or 6 or 7,000 kilograms of dry mass. So it's really not like the idea is empty. They're not that heavy.
By the time you're done setting up, you've got 2 landers, you've got 3 tugs, and you've got a station.
Yeah.
And that means that even though it takes a long time for the tugs, you've always got them cycling back and forth. And the tugs, if you're not using them to land on the moon to supply the moon landings, you can use them for other payloads. You know, people spend hundreds of millions of dollars moving things from LEO to GEO. You know, NASA charges a fraction of that price. They could actually make some money back on that part of it. Not enough to pay for the whole program, but something.
And the landers are recyclable. You're using
Right. They just go between the surface and EML2. So yeah, there's definitely a non-zero startup cost, and that's one of the things that we realized. But you know, we already looked at sorties previously, so we couldn't do that again.
Why do you need multiple tugs? I'm not
because the transfer time is so long. If you wait for one tug, your whole architecture just gets spread out over just a really long time.
Good.
Thanks.
Great job.
Thank you. Take your seat. Take your seats. I mean, this gives us an opportunity to look over the entire range of post-Apollo lunar missions. Let me just add while we're getting set up for this that you know, those of us on the faculty have long ago learned that the students are younger than we are and smarter than we are, but better dressed than we are. That's that's true. So thank you.